I try and make very good progress on any of these.
Okay, so let's check it.
I have a claim. Well, no, the claim is like obvious, but it's the proof that's hard.
Your claim is what?
It's just, and it only works for 3 and 4.
Okay, so want to say your claim?
Yeah, it only works for 3 and 4.
Your claim is it only works for 3 and 4, not for other numbers. But could you prove it?
No.
Okay, so let's try to use. I told you the most useful idea is what?
Small examples.
Small example. And we want to solve it by using a small example. Okay.
Mhm.
So here, for n3, we have 3 factorial 6. So what are the divisors?
1, 2, 3, and 6.
Yes, 1, 2. Let's try it like this. 2, 3, and 6. The differences are 1 less than or equal, 1 less than or equal 3, which works. So n3 is our first answer. For n4, 4 factorial, which is 24. What are the divisors?
1, 2, 3, 4, 6, 8, 12, 24.
1, 2, 3, 4, 6, 8, 12, 20. And if you write the differences, it is 1 less than or equal, 1 less than or equal, 1 less than or equal, 2 less than or equal, 2 less than or equal, 4 less than or equal 12, right? So n4 is our next answer, right? Now let's check n5. 5 factorial is 120. So how many divisors does it have?
How many? Let me check. 2 squared times 3. That's 12.
Yes, you can say it's 2 cubed times 3 times 5. You said 12?
Yeah. Oh, sorry. 4 times 2 times 2, 16.
16. So number of. But the divisors is 4 times 2 times 2. And you know the reason is what, right?
Yeah, 4 times 2 times 2.
And do you know, for example, why we multiply 4 times 2 times 2 to reach number of positive divisors?
Yeah.
Because you
It's
say 2 to the
exponents.
0 to 2 cubed, right?
Yeah.
Okay, so the divisors are what? 1, 2, 3, 4 is good, 5 is good, 6 is good, 7 not good, 8 good, 9 is good, 10 is good, 11 is not good, 12. We don't need to write the rest. Because look, it is 1, it is 2. It should be less than or equal to. Let me check. Oh, no, sorry, here. The difference here is 2, the difference here is 1, and that's a contradiction, right?
Yeah.
Do you agree we can say same thing for n6? Because for 6, again, here, we have 6 as a divisor, we don't have 7, we have 8, we have 9. Again, we have same problem, right?
Mm-hmm.
Agreed?
Yeah.
Okay. For n7, try to find which part we have problem.
It goes 12, 14, 15.
Yes, because we don't have. Also, you can use 11, right? 10.
There's no 11, right?
We don't have 11, 10, 12, 13 on. But the problem here is we don't have also 13. So 9, 10, 12, we have 2, 14, 15. We have 14, we have 12, so this difference is 1, this difference is 2, this difference is 1, right? So here, because we don't have 13, you have this problem, right? Right?
Yeah.
Okay, now because of this 13, you can reject n7 until which n?
Reject until 11 or until 10.
Why 10? Because look, for 8 we have same problem, for 9 we have same problem, for 10 we have same problem, for 11 also we have same problem, because look, this part is important.
Oh, yeah, 13 then.
Until which number we can reject?
Until n equals 12.
Yes.
So
Until 12, because until 12 is divisor, 14 is divisor, 15 is divisor, right? But 13 is not.
yeah.
So now try to find for n13 for which part you can find a contradiction.
33, then 35, then 36.
33, 35, 36. Because we don't have. So you can ignore 34 because of 17, right?
Yeah.
Do you agree you could write for 16? 16. We don't have 17. We have 18. But here our problem is 19, right? So we don't have 17. We don't have 19. Okay, that's okay. Let's keep writing. But here we have problem. The difference here is 2. The difference here is 1 because of 19, right?
Yeah.
Okay, so because of this 19, we can reject until which n?
Until n equals 18.
18, exactly. Now for n19, what's the first part that we have problem?
Probably the next prime number.
Yes.
22, 24, 25.
Exactly. Look, 22, again, we don't have this prime 23, we have 24, we have 25. Difference is 2, let's not equal 1. Contradiction here, contradiction, like contradiction here. So it is for n19 until which n?
Until n22.
Exactly. N equals 22. Now, let's consider 23. For 23, try to find the first part that we have problem.
57, 60, 62.
57, 60, 62. Fifty-seven is a
Wait, no, you don't have. Sorry, not 62. Sorry, that doesn't work. Not 62. You don't have that number.
Try to find first position that we have problem, okay? For example, 23 was the first position for this one that we have problem. Try to find in what's the first place that you get in trouble, okay?
Well, it's not 29. Because you have 20. You don't have 31.
And you have 23, 24, 27. You don't have 29, right? You have 28, you have 30. But our problem here is that we don't have 31, but 32, 33. It is our problem, right? So our problem is this. So we have this problem until what number?
Until. Wait, 28, 30. Oh, okay. Until 28.
Until 28? No. Until what number? A better number we can say.
Oh, okay. It's 31 is the important one. So 30.
Until 30. Okay. So, for example, for n31, what's the first place that we can reach contradiction?
Till 31. 31.
Which number?
36, 38, 30, 39.
Exactly. We have 36, we don't have 37, we have 38, we have 39. So 2 less than or equal 1. Exactly. And we reach contradiction until which end?
Until n equals 36.
36, yes. And we want to generalize this idea, but let me just check something with you. Do you know Bertrand's postulate is what?
It says that there's a prime number between, I forgot the bounds.
Yeah, it says if n is greater than 3, we have always, there exists p, that p is prime, at least one prime, that p is between n and 2n minus 2. Like, for example, between 4 and 8 minus 2, 6. Strictly between them, we have 5 as a prime, right? For example, between 5 and 8, we have 7 as a prime now, right? For example, between 50 and 98, we have lots of primes. For example, 53, 59, and so on, right? Okay, now exactly like this, you should try to reach contradiction for general n. Want hint or want to try first on your own?
Hint.
Okay, as you can see, always we are reaching contradiction for a prime minus 1. For example, 37 minus 1, 36. Here, 30, right? So, why? Because we reach something like this. P minus 1 is in our set. P is not in our set. And P plus 1 is in our set. And P plus 2 is in our set, right? By induction. Okay? So, now you can reach contradiction until P minus 1, right? It is like induction. Now we want to find next prime that has this condition, okay?
Okay.
So now you should apply here Bertrand's postulate and see, okay, what's the next step? What's the next place that we have a problem again like this? Use this one and solve. Exactly like the thing here we did, okay? I can say this part was 90% of the solution and only 10% is left. So try a bit on your own. If you couldn't, let me know to give it. Okay?
Okay. I don't know how to prove based on. I'm trying to prove p minus 1, but.
Want hint?
Yeah.
Okay, so for example, we reach until this p, and then for np, we cannot reject this, right? Because we have p minus 1, we have p plus 1, right? P plus 2 and so on. But I want to consider next prime, okay? Suppose it is q and there is no other prime. Do you agree this q is greater than what? Greater than, we can say greater than p less than 2p minus 2, right?
Yeah.
And we don't have this q, and it is the first prime that we have. After this, so maybe we have more primes, okay? But it is the first one that we want to consider. So do you agree we can say between them, all of them are our divisors? Because each of them is a composite one, you can divide by 2. And then, for example, it is a composite number AB, and both of them are less than P, right here. Agreed?
Yeah.
Okay. Now, and if we want to prove that why all these numbers are here, because we know they are composite numbers, so they are A. And I want to say A is at most, because N is P, I want to say A is at most P, B is at most. Why? Because otherwise, if one of them is greater than P, if, for example, A is greater than P, We know b is at least 2, then 2p, right? So ab is greater than 2p, and that's a contradiction. Because we know if we have a number here, a complex number, ab is greater than 2p, but we know ab is less than q, right? And q is less than 2p minus 2, agreed? So we can say we have all these numbers here as divisors, right? Okay, but we don't have q. We have q plus 1. Again, by similar thing, by something like this inequalities, you can say, because q plus 1 is even number, right? It's an even number. So you can say 2 is here, q plus 1 over 2 also is here, okay? Because q plus 1 over 2 is less than or equal p, okay? And because n is p, we have all divisors. Okay. Now you can say what? You can say, okay, q plus 1 is a divisor. Now q plus 2. If q plus 2 is a divisor, then we can reach contradiction, right? Exactly like here. Look, for example, here, 23 was prime, 25 was not prime, so we reach contradiction quickly. But sometimes, like 29, next number is also prime, so we should keep working on the next, okay? So we have two cases. First case is this, that it is a divisor. This one is divisor. Next one is that it is not divisor, okay? For the first one, we can say contradiction, right? Because the difference here is 2, the difference here is 1, right? So here, q plus 2, we have two cases. In the first case, we reach contradiction, right? Now let's consider second case. I told you, look, I said we don't have q. For q plus 1, it is even. We can say we have this as a divisor, but for q plus 2. When we check a small example here, 23 was prime, but 25 was not prime, so we reach contradiction quickly. But for this one, 29 is not prime. 21 is prime. Again, 31 is prime, so we should keep checking, okay?
Okay.
So here, I said if q plus 2 is not prime, if it is not prime, then it is a divisor and we can reach contradiction, right?
Yeah.
Okay, now, so because the difference here is 2, the difference here is 1, and 2 should be less than or equal 1, that's a contradiction for this part. But if q plus 2 is prime, suppose it is prime, and we know q is also prime. Okay, for this case, one hint or one to try on your own.
I'll try. So q's prime. Wait.
Q is prime. Also,
prime
q plus 2 is prime, because if q plus 2 is not prime, then it is a composite number, and you can write it as, for example, something a times b, and both of them are less than or equal to p, so it will be a divisor, right?
Yeah, but q plus 2 is not going to be a divisor. Right?
Here, in this case, q plus 2 will be a divisor in this case.
In the second case where q plus 2
yes,
is
q
prime.
plus 2 is not divisor, so here we've not reached contradiction so far, right?
Yeah.
Okay, so like a small example, try to see what we did and reach contradiction for this case. So try case 2.
So wouldn't it's like kind of just be the same thing, and q plus what's it called? Q plus 3 is a divisor.
Q plus 3 is divisor. Why q plus 3 is a divisor?
Because it'll be even, and then that number will be less than q.
Yes, it is even. Then what?
And then it'd be q. Now I have to see if q plus 4 is a divisor or not.
Q plus 4.
Then if q
plus 4 is what?
Yeah.
You said?
We have to see if this is a divisor, because the q plus 4 is odd.
Yes, odd. But why it is divisor?
Let me see if this has to do with mods.
Try to prove it's divisor.
Plus 2 and q plus 4 would have to be divisible by 3, assuming q.
Exactly, because it is not prime, it is not, it is prime, it is prime. So we can say q mod 3 is what in this case?
0.
Oh, if q mod 3 is 0, then q cannot be prime
Oh,
because
not
by...
q. Sorry, no. I thought you were asking q plus 4.
Oh, no, q. 2,
Oh,
because
2.
q and q plus 2 both are primes. So if q is 1, then this one mod plus 3 is 0, this one mod plus 3, so because of this, q plus 4 is 0 mod 3, right?
Mm-hmm.
Then this one is a composite number, okay? It's not prime.
Yeah.
Now, because it is not prime, we want to say that it is, if we say it is divisor, the problem will be solved, right?
Mm-hmm.
Now try to see why this one is not prime.
Why, which one? Q m equals p.
Q plus 4 is not prime. Now try to why it's a divisor.
Sorry, you're cutting out when you speak.
What about now? Is my audio clear now?
Yeah, it is now.
Okay, I said we proved that q plus 4 is not prime, right?
Mm-hmm.
Now we want to, so it's a composite number. Now we want to prove why it is a divisor, okay? It's not hard. Try to prove it's a divisor because it's a composite number, okay? For when n is p. Look, for p factorial, our n factorial now is p factorial. You should prove that q plus 4 is not, we know q plus 4 is not prime. You should prove that q plus 4 is the divisor of p factorial, okay?
Okay.
Okay, try. Okay, because I have another class, I should go try this one as homework and try previous one, and let me know if you wanted more homeworks, okay?
Okay.
Okay, any question?
No.
Okay, have a good day. Bye.
You too. Thank you.
Thanks. Bye.
But hello. Hello.
Hi.
Hello.
Hello, how are you?
I'm good.
Okay, great. See my screen?
Yeah.
Okay, last session, we were working on this USAMO problem, right?
Yeah.
Okay, problem 1. And it says n factorial divisors of n factorial. Then we have so n3 works, n4 works, n5 doesn't work. And we found, for example, some primes. For example, for 13, all these numbers, we said we have 16, 17, we don't have, we have 18, we don't have 9, we have 20. Difference here is 2, here is 1. Then we wanted to use Bertrand's postulate. So look, between n for n greater than 3, between n and 1 minus 2, we have a prime. And so okay, let's consider first prime that is not a divisor. For p factorial, we wanted to check n factorial, p factorial. So then we said q is greater than p, less than 2p minus. Then we said q is not in this. If q plus 2 is not prime, then we said, okay, it is a divisor, right?
Yeah.
But maybe q is prime, q plus 2 also is prime, and we want to prove q plus 4 is not prime because of mod 3. So we want to prove q plus 4 is a divisor. So how can we prove it?
Well, it's congruent to 0 mod 3.
Yes.
So q plus 4, you can write it as 3 times some number k.
Yes, q plus 4 over 3. You should prove why q plus 4 over 3 is less than what?
is less than Q. Right.
Is less than Q. No, if we
Because
prove it is less than or equal, what then the problem will be solved?
well, isn't it every prime up to Q is works, right?
We are checking P factorial, so it should be less than or equal to P, right? Look, we are considering what number? 1, 2, 3, 4, 2, P, right?
Yeah.
So 3 is less than P, so if we prove Q plus 4 over 3 is here, then this times this is a divisor of P factorial, right?
Yeah.
Why Q plus 4 over 3 is less than P?
Q plus 4. Let's see. It's less than 3. Q is less than 2P minus 2. So it's 2P minus 2 plus 4 over 3, which is 2P
2P
plus
plus
2
2
over
over
3.
3. We should prove it is less than
Yeah.
P, right?
Yeah,
It is
2P plus 2 over
equivalent that
3.
P is greater than 2, which is correct, because look, we proved for also until here, what factorial? Until 31 factorial we proved, right? You can say P is at least 31 or something like that. And also Q plus 4 over 3 is not equal to 3, because the Q plus 4 over 3 is greater than 3, because Q is greater than 9 minus 4, 5, obviously. Because we say P is at least 31 and Q greater than that, right?
Mm-hmm.
Right?
Yeah.
Okay, for this one also, for Q plus 2, it was case 1. For this one, Q plus 2 is not prime, right? For this one, how can we make sure that Q plus 2 is a divisor of P?
So Q plus 2 is an odd number. So given that Q plus 2 is not prime, I'm not sure what to say. Because I don't see a specific factor that it's divisible by. Other than that, it's Q plus 2 is composite.
Look, we said Q plus 2 is not prime, so Q plus 2 is a composite number, right?
Yeah, it's a composite number.
So we can write Q plus 2 as, for example, here, because we can say Q plus 2 is CD, right? And C and D are greater than equal to 2, right?
Mm-hmm.
Right?
Yeah.
Okay. If C is not equal to D, if we multiply 1 to P, if we prove we see C and D, then it will be proved, right?
Yeah.
Okay. So we want to consider two cases. Case 1, this case 1 to C is equal to D. Want to prove that C and D are here on your own or one team?
You mean here, you mean that they exist?
You should prove C and D both are less than P, less than or equal to P. If you prove this, then we see both of them and it would be a divisor of P factorial, right?
Yeah.
And it's not hard. Try to prove C and D are less than or equal to P.
So if one of them is, if C is greater than P and D is at least 2, then C times D is equal to 2P, which is greater than Q plus 2.
Exactly. For example, if D is greater than P, then CD is greater than equal to 2 times P plus 1, right?
Yeah. Or greater than
And
2P. Right?
we know that CD is Q plus 2, right?
Mm-hmm. Q is less than 2P minus 2.
Exactly. Q is less than 2P minus 2, so it's less than 2P. But here it is greater than equal to 2P plus 2, contradiction, right?
Mm-hmm.
So if we can write Q plus 2 as product of two numbers that are not equal and greater than equal to 2, so we proved, right?
Yeah.
Otherwise, it means Q plus 2 has what form? If we cannot write as CD, which C and D are not equal and greater than. So plus 2 has what 4?
Well, it can't be a prime. So wait, so you can't write it as C times D where C and D are not equal. So you write it as a square?
As a square of what?
A square of a prime.
Exactly. Only a square of a prime. So it is R squared, which R is a prime.
Mm-hmm. So I need to prove R is less than P.
R is if we prove also R is less than P, but we should prove also 2R is less than P. Agreed? Because we want to prove R squared is a divisor of P factorial. So we should prove 2R is less than P, right? Less than equal.
Mm-hmm.
Agreed?
Uh-huh.
Okay, so try to see, can you prove it?
Wait, can you explain why? Can you explain again why it has to be, why we're trying to prove 2R is less than P, not R?
Because look, if we have 1R, it's not, we want to prove Q plus 2 is a divisor, right? Case 1.
Mm-hmm.
So when you want to prove Q plus 2 is a divisor of P factorial, Q plus 2 is R squared, which R is prime, right?
Yes.
So if R is less than or equal to P, if you prove only R is less than or equal to P, then R is a divisor of P factorial, not necessarily R squared. Agreed?
Wait, but don't I want to just prove that Q plus 2 can be divided by?
We want to prove Q plus 2 is a divisor of P factorial, because look, we split it into two cases last session. Q plus 2 is not prime and Q plus.
Okay, I get it now. Okay, so you want two factors of R and P factorial.
Yes, we want to prove R squared is less than P. So in previous case, C and D were different. So if we prove C and D are less than or equal to P, because they are different, it's okay. But because R, they are same, so we need 2R. So we should prove 2R is less than or equal to P. Okay?
Mm-hmm.
So try to prove it.
Okay, so I got R squared. So I said R squared is less than 2P minus 2. So R is less than square root of 2P minus 2. So 2R is less than 2 squared root of 2P minus 2. So now I just want to prove 2 squared root of 2P minus 2 is less than or equal to P.
Okay, so let me write. You said it is R squared because 2 is less than 2P minus 2. It is less than 2P. So R is less than P is square root of 2, right?
Yeah, okay, so no minus 2 then. So yeah, R is less than P squared root of 2.
Sorry,
2R.
not a square root of 2P. So 2R is less than 2 square root of 2P. If we prove it is less than P, the problem will be solved, right?
Yeah.
Why it is correct?
I squared it, and then P squared minus 8P greater than 0.
P is less than 8. So when you want to prove, at first try to check all these things that P less than 2, okay? Check all P's that are less than or equal to 7 like this, okay?
And then that would be like,
and then write this.
That would complete the proof.
With our proof, we proved until 36.
For P,
we can say here P is
8.
at least 37. Agreed?
Yeah.
Okay. But you don't need to write all these things. Okay, you can check it. We need until P at this point, okay? So we proved this completely. Agreed?
Yeah.